Hi class, this is section R.8, nth roots and rational exponents. Part 1, properties of rational. Okay, so square roots we've discussed already. Back in section R.2, we looked at the square root of 1, the square root of 4, the square root of 9, and other questions like that that work out nicely. The square root of -4, for example, is not possible in the real number system since we can't take the square root of a negative. Okay, the third root of 1, the third root of 8, and the third root of 27 also work out nicely. Okay, so why do you think that is? If I make a table, my first column has the perfect squares in it. So these numbers I'm sure you're familiar with, 1, 4, 9, 16, 25, etc. The next two you might not be as familiar with, so it could be helpful to have a list so you can refer back to it. 1 to the third power is 1, 2 to the third power is 8, 3 to the third power is 27, 4 to the third power is 64. Okay, keep going, we'll get 125 and 216. 1 to the fourth power is 1, 2 to the fourth is 16, 3 to the fourth is 81, etc. Okay, so the third root of 1, third root of 8, and third root of 27 work out nicely because those numbers are perfect cubes. Is the third root of -8 possible? Why or why not? Okay, so we know the square root of a number. We can't take the square root of a negative number, but what about the third root? Okay, so our guess would be -2. Okay, and then we would want to check it. So if we're saying that the third root of -8 is -2, that would mean -2 raised to the third power should get us back to -8. So -2 times -2 times -2 does in fact get us back to -8, since the first two negatives cancel and leave us with +4, but then we multiply by one more negative, so our final answer is negative. Okay, so the third root of a negative is possible. All right, what about the fourth root of 16? Or the fourth root of 81, or the fourth root of -81? So we want to look now at numbers that are perfect raised to the fourth power. Okay, so 2 to the fourth power is 16. So we know the fourth root of 16 is equal to 2, because 2 to the fourth power would get us back to 16. The fourth root of 81 is equal to 3, because if I start with 3 and raise it to the fourth power, I will come up with 81. And what about the fourth root of -81? Okay, does -3 work? So -3 raised it to the fourth power, I'd have -3 multiplied by itself 4 times. I would come up with +81, not -81. So the fourth root of -81 is not possible. Okay, so the difference is the index, right? Are you taking the third root of a number, maybe the fifth root or the seventh root of a number? Okay, any odd index is possible. Okay, you could take the third root, the fifth root, the seventh root of a negative number. If it's a square root, fourth root, sixth root, okay, when you try to work backwards, you would have an even number of negatives, meaning that negative would cancel, and you'd always come back to a positive value. Okay, so again, the square root of a negative number is not possible, the fourth root of a negative number is not possible, but the third root or the fifth root is. Okay, properties of, so let's let n be greater than or equal to 2 and m be greater than or equal to 2 be positive integers, and let a and b be real numbers. Assuming that all radicals, we have the following three properties. So if we're taking the nth root of a times b, I can break this up as the nth root of a times the nth root of b. Similarly, if I'm dividing, I can break up the nth root of a over b as the nth root of a divided by the nth root of b. Also, if I start with the number a and raise it to the nth power and then take the nth root, I'll get the same result if I take the root first. So start off taking the nth root and then raise that number to the nth power. One thing to note is that although these properties work for multiplication and division, they do not work for addition or subtraction. So the square root of a plus b does not equal the square root of a plus the square root of b. Okay, so one example, let's say we start with the square root of 9 plus 16. Okay, so the square root is really considered a grouping symbol. So to evaluate this, you would need to work inside the grouping symbol first. You have to add those numbers together to get 25, take the square root of 25 to get 5. So this value correctly simplifies to 5. An incorrect way would be to break it up, write it as a square root of 9 plus the square root of 16, which is 3 plus 4, or 7. Okay, so 5 is the correct way to go. You'd have to add the numbers together and then take the square root. It's tempting, but we can't break up a radical when we're adding or subtracting. Okay, example 1, simplify, and we're going to use the first property that we talked about. Okay, so I have the square root of 18. Now 18 is not a perfect square, but I'm going to look on my list here, and I want to come up with the biggest perfect square that divides evenly into 18, and that answer is 9. So 18 is the same as 9 times 2. That first property tells me that I'm allowed to break this up, and I can write this as the square root of 9 times the square root of 2. The square root of 9 is 3. So my number simplifies to 3 times the square root of 2. Okay, let's do the same thing for the square root of 45. Okay, again, 9 is the biggest perfect square that divides into 45, since 45 is 9 times 5. Break this up to the square root of 9 times the square root of 5. Again, the square root of 9 is 3. So I have 3 times the square root of 5. Okay, part C. This time I have the square root of 700 times x. Okay, so 700 is not a perfect square, but 100 divides into it. So I'm going to think of 700x as 100 times 7x. I break this up into 2 radicals. Okay, I take the square root of 100 to get 10. So my answer simplifies to 10 times the square root of 7x. Okay, so notice that 7 does not have a perfect square that divides into it, and neither does x to the first power. So that's how I know that I'm fully simplified. Okay, similarly, I have 300x cubed. Okay, 300 is not a perfect square, but 100 is, and that divides into it. Also, this time I have x to the third power. So I'm going to think of x to the third power as x squared times x. And I'm writing my 3 in as well. So I get back to 300. Okay, so I'm doing the same thing, just this time also with a variable. Okay, so x to the third power. I want a perfect square. So x squared is the biggest perfect square that divides into x to the third power. Okay, and I know that by rules of exponents, when I multiply it, I have to add the exponents together. Okay, so I know those are equal. Okay, I now can write this separately. So I have the square root of 100x squared times the square root of 3x. The square root of 100 is 10. The square root of x squared is equal to x as long as x is greater than or equal to 0. Okay, since we're assuming all variables are positive, we can just write this as x. Good, and then I still have times the square root of 3x. Okay, and we're going to do some more examples where we have variables raised to powers. Okay, part E, I have the square root of 16, x to the 10th, y to the 6th, z to the 8th power. Okay, so if I work backwards, I want to have something here in parentheses such that when I square it, I end up with 16, x to the 10th, y to the 6th, z to the 8th. Okay, well, I know that 4 squared is 16, so I need to have a 4 here. I need x to some power such that when I square it, I come up with x to the 10th. And remember, if I have a power raised to a power, I multiply my exponents together. So this must be x to the 5th. Y would have to be raised to the 3rd power, and z to the 4th power. Again, this way, when I have my power raised to a power, I'll end up with y to the 6th and z to the 8th. Okay, so the answer here, again, take the square root of 16, since that's our coefficient, just to get 4. But now for your variables, we're really dividing them by 2. So I have x to the 5th, y to the 3rd, z to the 4th. Okay, and the reason why we divide these exponents by 2 is because when we check our answer, if I'm squaring it, power raised to a power, you multiply. So when you take a root, you must divide. Okay, good. Moving on to part F. Okay, this one I need to break up since 75 is not a perfect square. Okay, 25 is the biggest perfect square that divides into it, so I'm going to write my 25. X squared I'm good with since x has an even exponent. Okay, y to the 5th, I'm going to break that up as y to the 4th times y. Okay, and again I need a 3 along with that y, so 25 times 3 gets me back to the 75. I have my x squared, and y to the 4th times y is y to the 5th. Okay, so again, I like to write it this way. That way everything with the perfect square is together. So 25x squared y to the 4th is under the radical, and that's going to work out nicely. And then I'll be left with the square root of 3y at the end. Okay, so the square root of 25 is 5. The square root of x squared, again, since we're assuming we have positive exponents, the square root of x squared will be x. The square root of y to the 4th is y squared. Check it in your head. You're taking these values and you're squaring them. 5 squared is 25. X squared is x squared. And then y squared squared, power raised to a power, multiply your exponents together. Okay, and this gets multiplied by the square root of 3y at the end. Okay, part G, moving on to third roots. Okay, so now I'm going to look at my perfect cubes. So 24 is not on my list, however 8 is, and 8 divides into 24. So I have the third root of 8 times the third root, a third root of 4. The third root of 8 is 2. So my number simplifies to 2 times the third root of 4. Okay, 2 more. Part H, I have the third root of 54. So again, 54 is not on my list. Okay, 8 does not divide into it, but if you check 27, you'll see that it does. So I have the third root of 27. It's 27 times 2. Okay, x to the third I'm good with. Since I'm taking the third root this time, I'm good with x to the third, y to the 6th. And then, like I said, 54 is 27 times 2, so I need a 2 there, also under the radical. Okay, I'm going to break this up into 2 radicals. So I have the third root of 27 x cubed y to the 6th, and I multiply this by the third root of 2. Okay, so remember for this first guy, if I'm checking it, I want something that I can then raise to the third power and come up with 27 x to the third y to the 6th. Okay, well, 3 to the third power is 27, right? I get that from my list over here. X to the third power is easy, right? So x cubed is going to give me an x cubed here on the right. And now for y, I want my exponent such that when I multiply it by 3, I come up with 6, right? So this must be x squared. Again, power raised to a power, so you multiply those exponents together. Okay, good. So this is why I was okay with both x to the third and y to the 6th, okay? Because I know that taking the third root means I want to divide these exponents by 3. And they both work out nicely. They're both divisible by 3. Okay, so my final answer is 3xy squared times the third root of 2. Okay, and finally, part I have the third root of 3xy squared divided by 81x to the 4th y squared. Okay, so 3 and 81 are not on my list of perfect cubes. And then I see for my x and y, these are all raised to even powers of 1, 2, 4, and 2, but those are not divisible by 3. Okay, but remember, I can simplify my fraction first. So let's do that. I have the third root of, so I'm going to simplify 3 over 81. Well, 3 goes into 81, whoops, 27 times, so I have a 27 in the denominator. X divided by x to the fourth, I have more x's in the denominator, okay, and then these y squareds are going to cancel. So this is a much better problem, okay. The third root of the numerator, the third root of 1 is 1. The third root of the denominator is going to give me 3x. Okay, since 27 is on my list, and x cubed is a perfect cube. Okay, so even though part I looked like it was going to be messy, once I reduced my fraction, it actually worked out nicely because it was a perfect cube. Okay, good. These are the two that you are going to complete and turn in through Canvas. Okay, so in part A, you're going to simplify the square root of 27, x to the 6th, y to the 8th. And then in part B, we have the third root of negative 27, x to the 6th. Okay, good luck. Let me know if you have any questions.